Welcome to Module 3 of CS 179, Networking 1. And we're still, of course, using the Managing and Troubleshooting Networks by Mike Myers from McGraw-Hill. And we're going to talk about Chapters 4 and 5, Ethernet. So we're going to be covering CSMACD, 10 base T, 10 base FL, 100 base X, 1000 base X, and gigabit Ethernet. So let's talk about some of the ways that data can step out from the computer and into the network to be transmitted. One of those ways is called contention, and it will transmit whenever the circuit is free. So whenever the circuit says, in this case, it could be the switch, it could be the other computer. Whenever it says, "Hey, I'm free," then the sending computer will say, "Okay, I'm sending it off." And when collisions do occur when more than one computer transmits at the same time. So hopefully you don't have that happen. But when it happens, it does happen. You need to resend the data. The computer does that automatically. It needs to determine which computer is allowed to transmit first after the collision. So somebody's got to be in charge. And in most cases, it's going to be the switch communicating with the network cards. And it's very commonly used in Ethernet LANs. Can be problematic in heavy usage networks. Another way would be called polling. It's the process of transmitting to a client only if asked or permitted. So the client stores the information to be transmitted. The server periodically polls the client if it has data to send, and the client, if it has any, sends the data. So basically, the server is going to ask, "Do you have anything for me? Do you have anything for me?" It goes through all the different computers, and if they do, they go ahead and send it. If no data is to be sent, the client responds negatively, and the server moves on. So you've got roll call polling and hub polling, also called token passing. You would use in token ring. Roll call polling, check each client consecutively and periodically, as I mentioned, and to see if they want to send any data. Needs a timer to prevent lockups by client not answering. So if client A doesn't answer, it won't go on to client B unless you have a timer that times out if client A is having an issue. Error control. This is, of course, very important. Handling of network errors caused by problems in transmission. There's going to be errors when sending data. There can be network errors. Can be a bit value changed during transmission. So remember, you only have ones and zeros. So if that 0 flips to a 1 or 1 flips to a 0 because of magnetic interference, then it could change during the transmission. Controlled by network hardware and software. And you can equate this to human errors. It could be a mistake in typing a number or controlled by application programs. Categories of network errors are corrupted, data that has been changed, or lost. Can't find it, just goes off into the ether. So what could cause these errors? Well, there could be line noise or distortion, more likely electrical noise, undesirable electrical signal, just not strong enough or too strong, introduced by equipment and natural disturbances. You could have an earthquake, electrical storm, lots of different things. Degraded performance of a circuit. Maybe the circuit itself is going bad. And you could have a manifestation, of course, of extra bits, slip bits, or missing bits. This could even be caused by the sun. As electrons and things like that come through the atmosphere, they can flip those bits as well. Different ions and things like that. Major functions of error control. You've got prevention, detection, and correction. So detection techniques are parity checks, checksums, and CRCs. So parity checks, basically, if you have 8 bits in your packet, it uses a 9th bit as a parity check, and it uses a mathematical formula to either have a 1 or a 0 at the end, and that's how it does parity. It's actually far more complicated than what I just said, but that's the easy way to describe it. Checksums adds up various different amounts of bits in total and make sure they match the amount that was expected. And CRC, those can happen. Those types of errors can happen when you don't transmit at the expected speed or the expected duplex. So if you could do full duplex or half duplex, and we'll talk about that more in future modules. But if you don't match up on both sides, then you could end up having CRC errors. So once you have those errors, what do you do? So once detected, the error must be corrected, of course. Some of the different correction techniques are to just transmit it again. Simplest and least expensive way to do it. It could be corrected by retransmission of the data. Receiver, when detecting an error, asks the sender to just retransmit, often called automatic repeat request, or ARQ. You're going to see ARQ on some tests coming up. Forward error correction. Receiving device can correct incoming messages without transmission. So if it has good parity, it might be able to fix it on its own or using some other technique. 802.3. So as I mentioned earlier, 802 is 80 is 1980, and 2 is February by the IEEE, and that's when they first convened to create these different standards. And .3 is Ethernet. So it's the most widely used LAN protocol, developed by Digital, which was bought by Compaq, which was bought by HP, Intel, and Xerox, and it's now an IEEE standard. Uses contention-based media access. We talked about contention earlier. Byte count data link layer protocol. It doesn't have a transparency problem, and error correction is optional. So here's an 802.3 or Ethernet frame as it is getting ready to be transmitted. You've got all these different pieces to a frame. So, of course, you've got the data itself. That's going to be the biggest part of this. You've got your CRC. That's your communication speed and bandwidth and duplex and things like that. Over here on the left-hand side, you've got the destination address. This is where it's going, followed by the source address, just so the destination can confirm where it's coming from. Then you've got the number of bytes in the message field, information about that, make sure it matches, so that way if there's an error it'll say, hey, how many bytes was I supposed to be, and then that's how it knows. Then you've got the LLC control, and it's used if you have a VLAN. Now, if you only have one LAN subnet, then this will be blank. But if you have multiple VLANs, and it says, hey, which VLAN number are you? And then you have snap control. It's used to control information such as the type of network protocols used, network layer protocols used. So that's what an entire frame looks like when it's getting ready to be sent from one computer to another. The point-to-point protocol is byte-oriented protocol developed in the 1990s. It's commonly used on dial-up phones, so you're not going to see this much anymore. It's designed mainly for point-to-point phone lines. So this is what that looks like. And I'm not going to go into too much detail on that because it's not used much anymore. But it is in the book, and you might see a test question about some of these things coming up. Throughput, a more accurate definition of efficiency. It's total number of information bits received per second. So it could be kbps, kilobits, it could be megabits, it could be gigabits. Now we measure speed in bits, not bytes. So never say you're sending something at 100 megabytes. It's not true. That would be 800 megabits. So by 8 is what byte means. So speed is measured purely in bits. Now storage, like your hard drive space, that's measured in bytes. So make sure you don't confuse that. So it's very complex to calculate. Depends on lots of different things. Transmission efficiency, the error rate, such as 10 base T had a very high error rate, but now we've gotten much better at 100 and 1,000. The number of retransmission times on average that needs to be sent. The transmission rate of information bits, also called TRIB, is used as a measure of throughput. So now you have media access control with shared Ethernet. It uses a contention-based protocol called CSMA/CD. And as you can see, it stands for Carrier Sense Multiple Access Collision Detect. Frames can be sent by two computers on the same network at the same time. So if they collide and destroy each other, it can be termed as ordered chaos. It tolerates these things, and it just automatically retransmits them, rather than avoids them, such as CSMA-CA. So CA will avoid those things. Now, CA is slower, but you have less retransmits and less corrupt data. CD is faster, but you end up with a lot more crashes. So CSMA-CD, let's break that down. The carrier sense, the CS part, is a computer listens to the bus to determine if another computer is transmitting. It transmits when no other computer is transmitting as far as it knows. Multiple access. All computers have access to the network. Collision detect, declared when any signal other than its own is detected. If a collision is detected, to avoid a collision, both wait a random amount of time and then resend the message. And you hope that they don't wait the same amount of time, which is certainly possible, but not likely. So, media access control with switched Ethernet, each circuit shared by a computer and the switch. It still uses CSMA/CD. Multiple messages can be sent at the same time. Computer A can send a message to computer B at the same time C sends to D. So these two computers can send frames to the same destination at the same time. Of course, you still have the same risks, but it will move faster when you can have multiple computers sending at the same time. So you have a performance, you have shared Ethernet versus switched Ethernet. Shared Ethernet, which was typically used in 10 base T, had you could only get about 5 megabit speed because it collided all the time. Now, shared Ethernet was used with hubs. Switched Ethernet uses switches, so it runs up to 95% capacity on 100 base T. Now, I realize that most of our networks are now 1,000, but this is the technology where it was introduced. So, twisted pair Ethernets. This is where the cables are twisted around each other, and this is how most of our Ethernet cables are set up. So, with 10 base T, you used Cat3 and Cat5, and that was unshielded twisted pair, or UTP. It was very inexpensive. It ran for about 300 feet, or 100 meters. And, of course, it lost out to 100 base T. So 100 base T uses Cat5, unshielded twisted pair. Again, you can still use shielded, it just costs more. Also called fast Ethernet. That is a quiz alert. It replaced 10 base T in volume. Of course, it's way more common today. Now, Cat3 is still heavily used in telephones because telephones don't need that great a speed. But you can use also Cat5 if you wanted to with telephones as well. It's just Cat3 is going to be a lot cheaper. So, combined 10-100 Ethernet, some segments run 10 base T and some run 100 base T. So, switches are designed now to step down to 10 base T when it is required. Fiber optic based Ethernets. So 1,000 base T, gigabit Ethernet. Maximum cable length is only 100. Well, actually, this part here is not going to be fiber. This just kind of bled over from the previous slide. So this is still going to be using the Cat-based Ethernet cables. Maximum cable length, again, is 100 meters for Cat5. The fiber optic based runs 440 meters. 1,000 base F, 1 gigabit fiber. So you can really get some good speed there. But again, it is fiber when you see the F. 10 GBE, 10 gigabits per second Ethernet, uses fiber and is typically full duplex. Well, most everything is full duplex nowadays, but every once in a while you'll find one that runs at half duplex. Half duplex, of course, can only run one direction at a time, whereas full duplex can run two directions, both back and forward at the same time. 40 GBE is 40 gigabits per second, uses fiber, and is typically, again, full duplex. So here's a quick summary. You've got 10 base T at 10, 100 at 100, 1,000 at a gigabit, 1,000 F at 1 gigabit, 10, and 40. And those will show up on some of your tests. So to summarize, we've got, we talked about CSMACD and 10 base T, 10 base X, 10 base fiber, and gigabit Ethernet. And thank you for joining us. We look forward to Module